we will start today with the typed lambda calculus. Okay. So let me share my screen. And I don't have enough notes, I don't think, to fill whatever, an hour and a half, but we can keep going. So, I part of, I have something of a dilemma here. I mean, there is, well, there's so many different presentations, and I thought, okay, look, I'm going to go with Pierce again, right? This book. And I'm going to just do his presentation. And once again, I really dislike it. I don't, it's not, I'm not sure why it's so clumsy, but it really is. So then I turned back to, now, then Barendrecht's book is essentially almost all, let me just look. Barendrecht's book, The Bible on Lambda Calculus, I think has a little section, there we are, in the back. That might be the best reference. In terms of kind of just the classic presentation of the material. But, it's also one of the densest ones, and I don't know, it's kind of, one of the reasons I don't like him is also one of the reasons I don't like Pierce is that they kind of assume everything is automatically renamed. So this is a book that Finley pointed me to at the beginning of the course, and it's actually a very nice book. The more I read it, the more I like it. It's kind of a mixture between the more classic presentation of this material, kind of like the more mathematical presentation, and, Pierce, who's kind of like trying to be more programmatic. I mean, he's kind of like trying to introduce the math in a way that's really just almost the programming. It's almost as if you take his implementation code and then work backwards from that to write the book. So this notation that I'm using is a little bit of a, I'm sorry. It's a little bit of a mixture of Mimram's book and Pierce's book. So anyway, so the syntax for, and I know, like, for example, I know that that Simon finds that kind of like annoying if we don't have one text to go from, and maybe it does make it harder to learn if I'm not using exactly the same notation. I hope you don't feel like I'm picking on you, Simon. I kind of understand your position.
So it's for the first couple of weeks having a core text was useful, but I have broadened out to use a selection of texts now.
Okay.
So I don't disagree with you. Just the first couple of weeks, it was uncomfortable for me. But now I have that grounding. Yeah, I completely agree with having a selection.
Okay. So now let me just say that this is starting on page, I think, 104 of Mimram's, 173 of Mimram's book. And I really like this presentation so much better. I mean, I started going through Pierce, and I don't know, there's stuff in there I don't actually quite get, like, when he talks about what values are in his type lambda calculus. The only values that he has are lambda terms in the pure simply type Lambda calculus. And I think he even admits that, with his presentation, there are no well-typed terms. I think he says that, like in his presentation, until he adds some base types. So he misses something in the type language. All right, well, let's start looking at it. In any case, it's always, this part is the same. You've still got exactly the same things. You have variables, you have abstraction terms, except that now what you do is you add in some way an annotation to the variable to say what the type of the bound variable is. And you have application term. So, I mean, it's kind of, usually I write them the other way with abstraction coming last, but obviously it doesn't matter because this means or. A lambda term is a variable, or it's an abstraction, or it's an application. So or is commutative and associative, so we don't, it doesn't matter. Now, what is this T thing? And this is one of the things when I'm teaching Haskell or OCaml or, any typed functional programming language, you've got two languages going on. You've got, these are the terms that are computation terms. These are the terms that you actually compute with. And the types, it's a separate language. And so this is what Pierce doesn't have. He just says everything is a TROT. So he has like no base case. So it doesn't, I'm not sure why he does it that way. But anyway, that's what he tries to do there. He does present types for lambda calculus after a chapter where he's talked about typing arithmetic expressions. So perhaps, then later he adds like base types instead of type variables. And to be consistent with MemRam, these should be capital A, B, C, D, so forth, A1, and so forth. So, like the question that I always ask in people in like 4780 is like, we're in principles of programming languages, as we're moving along and we've added variables, and I say, what's the value of X? And people, will say, well, some students look like deer in the headlights, and, they don't know. And there's a good reason they don't know, because they don't have enough information to say what the value of X is out of the blue. Like if we're working in some context of a proof or a program, you could say, oh yeah, X here would be this, but without that, you can't. So how do we keep track of that stuff for the purposes of figuring out what the type of X is? So it's not the value, we want to know the type of some things. And so we have contexts, and the context is usually written as a gamma, and it's either the empty context, there's nothing, it just contains no pair, or it's the context with a variable X. So that's one of the variables from the computation language, together with a T, which is something from the, it's a type expression from the language of types. So we have these two languages. We have the language of the computational language, we have the type language, and now we have like a data structure essentially to keep track of, as we're trying to figure out what the type of a term is, we kind of like need to remember some things as we're going along. We say, oh yeah, we said X had type A. Okay, add that into the context. So you'll see in the typing rules how that works. But, and So we write gamma x to denote the rightmost pair x sub j colon t sub j if gamma is this, sequence x1 colon t1 dot 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 xk colon tk. And it has to be that the x is syntactically identical to the x. X sub j has to be the x that you're looking for. So it's the rightmost pair furthest towards the end, because we're adding on the end and we're going to treat this like a stack. So it's just like a backwards list. You're adding onto the right side and you're taking off the right side. Now, gamma sub x is undefined if there is no x in the domain of gamma. So the domain is all the first elements and the range is all the second elements. And if you look at the domain, if x is not there, then this thing is undefined, and so it's kind of not. We'll see in a second what it means. So now, one of the things about the MIMRAM book is, and I'm almost regretting not having followed it from the beginning, but it had just arrived when we started. So I've had a chance to read a lot of it now. But in this book, Program Equals Proof, one thing he does is he does logic first. And then he does typed functional programming, a little short thing. And then he does a few chapters on logic and different kinds of logic. And one of the ideas that comes from from the proof systems that you can use to present a logic is something called a sequent. And they usually look something like that. Sequent, the term sequent is used in different formal systems in different way. But here, a sequent is a triple. So you have a so you might say like, oh, what? This like it's really, in a way, maybe this is what I'm trying to find my pen for my Wacom. Did I put it away? No. It's kind of, maybe this is what, in a way, Pierce maybe was trying to get away from, which is, oh, come on, I just had it. Oh, I guess I didn't just have it, but I haven't used it this morning. I was using my pen for my, oh, there it is. So the one thing I guess that I kind of want the pen for is to show you that, okay, it's a little bit maybe like it feels jargony, like if you don't know what a sequent is, but he kind of tells you here. He says a sequent, where's the pen? Oh, I gotta turn on the Wi-Fi or the Bluetooth or whatever that Bluetooth. All right. I apologize for this interruption. Okay. So, I mean, when he says it's a triple, I mean, as a data structure, you can literally think of it as a triple where you have, let me write out here, where you have gamma paired with a term t so this is, this is a lambda term. This is a context. And paired with a type. Now, I wonder why he says that. It's not necessarily, oh, no, it's not necessarily a type variable because we have rules that look like this. So this is a type expression. So, you know, if you're implementing this in Haskell, for example, you would just say, oh, okay, this is what a sequent is. It's a triple. But for historical reasons, you know, it's written in this other way. And this notation, this turnstile here is in logic, it's often the case that you have like two symbols, one like this, which somehow or other means like provability. Now my display is getting provability. So this normally means something like provability, and this is models or something is true in a structure. You know, you have some formula over here. Oh, I shouldn't have written that so close. And you've got some M over here. And here we have like gamma, and then we've got some kind of formula. Some kind of syntactic thing here. And for us, it's actually a pair, T colon, and I would really maybe prefer to write it T colon capital T. So this is something of this form where this is, you know, a lambda term and this is a type expression. And oh, maybe this phi is looking like the empty set to you. There's so many pitfalls. So this is that, you know, phi is provable from gamma. And this one here is saying that phi is true in the structure M. So these are ideas from logic that then get translated over largely because of Curry-Howard. So in fact, in a really precise way, we'll see a little bit later. But so this is a triple. And now what we want to be able to do is we want to be able to prove, and so this thing here is a relation, you know, so really this turnstile in our case is a relation between a context and a pair, which is a term. I guess I should write lambda there. It's a lambda term crossed with a type. So I didn't write subset. So this thing here is a relation. Turnstile is a subset of this cross product. So it's a relation between context and lambda term paired with a type. I'm wondering if I really want to say it that way. It's more like the lambda term is in the relation to the type, and the context is kind of more like a parameter to this. In gamma, lambda is in the turnstile relation to t. No, I'm sorry. I do want it like this. And I guess what I want to say is that colon, this thing here, meaning has type, is a subset of lambda terms crossed, paired, Cartesian product with types. So this is has type. You read this one as like has type. And this one means that there is a derivation. The turnstile means there is a derivation. Oh, come on. And so, just like in other spaces that we, or discussions, what we're going to do is we're defining turnstile as being the smallest relation on these for which these rules show you how to build a derivation. So I still kind of don't like saying it's a relation between gamma, and maybe I want to say gamma and lambda is the left part and tau, but I guess it doesn't really matter. Any questions on this? So let's look at the rules, but first, is there any question? This is just a triple, and it's got three things. If you have a representation of a context, like a list, for example, and you have a representation of a lambda term as like a data type called lambda, except now it's been extended just the littlest bit to add an extra part in the abstraction, which is the type of the variable. And then type expressions are new, but this is an easy thing to implement in Haskell. Questions? Come on. Everything's perfectly clear. All right. And so the other thing here is that this is just kind of notation sort of adopted from logic. And this is usually has to do with provability or derivability. And this one has to do with something being true in some kind of structure. Okay, so what are the rules? Pierce writes this first. So here's Pierce's name for these rules, and here's Mimram's name for these rules. And Mimram's name is actually coming from the natural deduction naming of logical rules are either divided into introduction rules or elimination rules. Although I have to say, in some way, I feel like he's got them backwards, but okay. So what is the rule for the axiom? Well, when does X have maybe Pierce's way of writing this rule is better. What Pierce says is Pierce says in the context gamma, X has some type T if gamma sub X is equal to T. But this is the same thing. It's just maybe a little bit harder to read. It's like this is true. And like I said above, this is undefined if X is not in the domain of gamma. So it's like the only way that you know that a variable has a particular type is if it's been previously entered in gamma or whatever. You were given a gamma that has it. So if you had like something like, okay, if gamma was something of the form, well, then usually you don't write like the list things around it. But let's say you had something that looked like, you know, like X colon A, Y colon A arrow B, turnstile. Oops, I want that to be capitalized because I'm going to use capital lower letters in Latin letters lower in the alphabet for types. So turnstile, that proves two things. It proves that X is in A, or alternatively, if I had the same context, that would prove that Y is in A arrow B. So when you're trying to figure out the type of a variable, this is the same as when I say to the student, what's the meaning of X? And they go like, I don't know. And I say, you need some kind of data structure to remember what you know about X. And if you don't know anything about X, then you can't possibly say what the value is. But this is the same thing. So think of the context as just a data structure to help you record information as you're building a derivation. Or you can start out with a gamma, like, you know, just this. This is just true. Here's my gamma. Here's my variable. Here's my type. This is just true. It's an it's an instance of this axiom. But, you know, I guess the thing I'm trying to say is that if you tried to say, for example, I'll go over here. If I tried to say something about, I'm up here. All right. So if I said like, okay, I have a context that says X is in A and Y has type B, and I try to prove something about Z, there is no rule to allow me to prove this from this context. So, I mean, it's really a very simple idea. You just look and see, is this thing already known? If it is, then it's true. Otherwise, it's not derivable. Otherwise, there's no derivation. Okay, so now, in a way, you know, these rules are really nice because, and we should, you know, and this is the reason we should maybe, you know, the people who are so, you know, a lot of people are really strong. You got to show the types. You got to show the types. And that's because I think this, in a way, these two rules explain the meaning of application and abstraction. So let's look at the application rule. If I have some M applied to N, and I want to show that it has a type B, well, if M is applied to N, then it better be the case that M is a function of some type. It doesn't make sense to apply like a number, for example, we have is lambda expressions. So it doesn't make really anything, you can't tell much about um, for example, if I had if I had x, y, x applied to y, well, I can't really tell that much about it unless I could pull the x off and somehow in my context, I could show that x was a function type and y was the proper type as an input. So this is the thing about the second thing. It has to be the type of input that M is expecting. And if N is the right kind of input for M, then M applied to M has the output type of M. Does that make sense? I don't, come on, eraser. All right, there it is. No comment. Okay. And then the abstraction one maybe explains to you what an abstraction is. An abstraction, lambda x of type A dot M, is a function from A to B if, when I add the assumption that this x has type A, I can show that M has type B. So if I want this to be a function, then I say, okay, just assume that you've got X and that you've received an X, whatever it is, and it's something of type A. And now show me that M has type B. And so then that means that you have an A arrow B for lambda X of type A dot M. All right, so we're going to do some proofs. But there's a few things to note. I mean, I mentioned this before. You've got the computational language, and then you've got the language of type expressions. And what's going to happen in the polymorphic lambda calculus is you're going to actually add like a lambda in the type language. Right now, the type language basically only has type variables and the arrow, you can arrow types. Now, um, I guess a few other remarks about this are that if you're writing Haskell code, there really are two languages at play. There's the computational language, which is Haskell code, but in this case, they're the lambda terms, and the language of type expressions. And so we have these two languages in Haskell, and a lot of people, students, when they're starting out, they want to write types where you actually need computation terms, or they write lambda terms where they actually, or whatever, a Haskell program, right? So lambda term is equivalent to Haskell program, and this is the types. So there's two separate languages, and the main thing to remember is that the colon, which means has type, the left side thing, the thing on the left side is a computation term, and the thing on the right hand side is a type expression. Now, this is another thing that can be confusing if you don't realize it is that if I have L applied to M applied to N with no parentheses, the default is, that means apply L to M, and whatever the result is of that, apply that to N. So what we say is function application associates to the left. So you group parentheses from the left to the right, and that, but arrow associates to the right. So A arrow B arrow C with no parentheses means A arrow and then B arrow C. And so you can sort of see, you can try other possibilities, and you'll see that this is a very natural one. Like L applied to M applied to N should mean that L is something that takes two arguments, say of type A and B, and returns a C. So if I want to write down a little proof, a little type derivation of something without writing down a bunch of parentheses, then this meshes together, behaves nicely with this. Oh, and these are the so-called church style lambda terms, because in the church style lambda terms, we actually annotate the variables in the abstraction with the type. Okay? In the so-called Curry style, we don't use labels. So you just have the lambda terms look exactly the same as they do in the untyped lambda calculus, but you use the rules to kind of figure out the type, the rules to figure out the types of things. Now, Haskell and OCaml use the Curry style rules. You never have to write, well, maybe not never, ever, but like in 99.9% of the time, the type inference algorithm can take a term which doesn't have these little annotations in it and figure out the correct type of it. In fact, it not only figures out a correct type, it figures out amazingly the most general type. And we'll see what that means in a little bit, but it's kind of like the most abstract type for that expression, which is one reason, I don't know, when I was working the other day with on going over some of the homework stuff with Jessa, and I'm not sure if Simon was still there or not, but I was writing some code. Some people apparently students come out of 3015 thinking you always have to write down the type before you write the definition of the program, but really you don't. And in fact, it's almost better not to, because sometimes you might write down the wrong type, even though your program is what you intend it to be, and then that's going to come back and complain to you. It's almost better to write your Haskell code, write the program, and just think of maybe write the type as a comment. And then if your program loads, look at the type that Haskell has for it, because occasionally it will surprise you and give you a more general type than you were thinking of, which means that that program is useful maybe in different contexts. If not, you can write the more specialized type where you intend to use it, and then anyone who uses your function won't be able to use the more general type. So I don't know, did any of that make sense, or do people have a clue what I'm talking about? All right, Finn, you're something of an expert Haskell programmer. Did what I just say make sense?
Yeah, to me, it made sense.
Okay. So I don't know. Kyle, what about you? I mean, I'm not
about 50-50, I suppose.
Okay, right. I'm not trying to like figure out if you're, dumb or smart. I'm trying to figure out if what I'm saying makes sense to you, because otherwise maybe I should explain it a little bit more. Zach, what about you?
I think so. I'd have to try it out to know for
Okay.
certain.
I mean, I don't know. I could show you a simple example maybe by going to Haskell, but I don't want to get drawn too much into programming in Haskell, but let's say, I don't know. Let's go look at our lambda.hs. Okay, so look here. I mean, this remove function.
Your screen share is off. Just a heads
Oh,
up.
right. Thank you. Okay. Thanks. Like here is this Lambda code. I don't have the type written down for remove there. Now, oh, come on, stop belling at me. Can you hear that bell?
Yeah, very lightly.
Well, it's really loud in my ears. Okay. Start the interpreter and I'll load lambda.hs. What? Line 41. Oh, maybe I was editing this and. Okay, so what's the type of remove? Well, remove is extremely general. I mean, I'm thinking I'm going to use it down in my free variable thing here where X is a string and the argument which is left off of here actually on both sides, this is an example of eta reduction. Right? I could say, I could say this, and this is the same program, but Haskell programmers learn that, oh, if it's the last one, we don't actually need it because remove at filter not equal to X is going to be a function that's expecting a list of things of type X. And so if you look here, the type is very general. It basically just says, okay, remove is as long as I need to be able to do an equality test. So, or not an inequality test, but that means I can check equality. So as long as A is a type for which I can figure out whether or not two things are equal, then remove has type A arrow list A. It's waiting for a list A, and it's going to return a list A. And so we could say, remove. So it works with numbers, even though we might have, in this context, if you were writing this program, you might say, oh, wait, remove has type string, arrow, list of string, arrow, list of string. And the code will still load. But now remove has a more specific type. It's the type that I said here, whereas the other one was much more general. Now, sometimes, in software engineering circles, they might say, yeah, no, this is better. And in fact, I should probably define a type called, var, which is just a synonym for string. And then use var in here, everywhere, and then change this to var and this to var. And then we're more specific to this particular type, but I guess I don't really know how I feel in that case about that. So I would say, usually just let the type inference algorithm in Haskell figure it out. And then if you want, and actually you might get it wrong. You might say, oh, well, I mean, filter, if you look at the type of filter, that'll tell you kind of the type. Oh, but it says A to bool. But see, then I'm using not equal x in here as my function from A to bool, right? That's expecting an argument, and it's going to return true if it's equal to, or false if it's equal to x, and true otherwise. So anyway, that's what I'm talking about. Does that make it clearer? Zach? Kyle?
Yeah, it
Yes,
does
sir.
for me.
Jessa, are you with me? Okay. Let's take it's like 2:05. Should we take a little 5-minute break or something? I wouldn't mind going and stretching my back.
Yeah, 5 minutes works for me. Thank you.
I sit in this chair too much. All right, let's take a 5-minute break. And I will pause recording. Somebody remind me when I. Okay. Oh, so what I wanted to do now is I want to, I guess maybe I could just do it here if I share my screen. I mean, we need to see the rules to be able to do some sample derivations. And so here's the rules. And so, I don't know, I guess I have enough room on the sides here to try to do it. Okay, so let's look like the simplest lambda term with no free variables is, so first of all, any closed term, so a lambda term with no free variables should be typable in the empty context. So we start out with the empty context, and then I look at the term lambda x, and I'll just label the thing with an A, and I'll say lambda x dot x. Now, the interesting thing about this is that, I mean, I kind of know that this has got to be an A arrow something, but I don't necessarily know yet. So I look over here, and I'm using this rule, and this is empty, and this is x. And so I put this x up over here with an A. So I add that into the context. So I'm adding this x colon A into the context. And now I got to show that x has some type. And the way that Memram writes it, it says, okay, just apply gamma to x. And so here's my gamma, and I apply that to variable x, and I'll get back A, and that is just an axiom. So now I know something, how to like fill in this down here. That has to be an A. So these rules have kind of like information flowing through them up and down. like, well, and from left to right. So like here, like, you know, this information comes over like that. And in this one, this goes up and this goes up and this goes up and this goes up. And then information goes from this one connected to that one to be able to give me this, right? I need to be able to link this, that the input type, the argument has the right type to be input to M. So I can't figure out B until I figure out all this stuff. And then here, again, you've got like this information is going up and this information is going up and this is going up. And this comes from here, but this comes down. And in our case, when this is X and the only thing that we have in our context is that X has type A, we get back X has type A. So what if we do another one and this shows, so first of all, so this is a full derivation of this sequence on the bottom row. Does that seem okay? How you build these things? You apply these rules, and the rules kind of tell you the parts that you don't necessarily know when you start. No questions. All right, let's look at another one. This one maybe is interesting. If I start with the empty context, and I want to show that like lambda x dot a, lambda x dot b x. So what do you think the type of this should turn out to be? I've got my best Moore method hat on now. I need to go get a hat. What's the type of this term? Yeah,
what's it be? A arrow B arrow B.
Yeah. Okay, so let's see though how we build the proof. So all we know at the beginning of this proof is that we know it's going to be A arrow something, and now I add, for this, I add that, okay, X has type A, and now I have to show the type of lambda X, where X is of type B dot X has some type. Now, let me try to fix up that writing there. So the rule that we applied here was arrow elimination or arrow E, and then I can apply, and so now I know actually that the B, it's a B arrow something, but I still don't necessarily know what goes here. So I can say, okay, do arrow elimination again. And so now I've got the old context says X colon A. And now I pull this one and add this to the context, X colon B. And now I have to show what the type of X is. And this rule says, okay, apply gamma to X. And applying gamma to X means get the rightmost one. And so this has to be a B. And so now I can bring that down, and this must be a B. And now I bring down this whole B arrow B type, and this has to be B arrow B. And so we got the answer that, oh, and this is, like an axiom. I just noticed though that technically the way that I've written this, trying to follow Pierce and then follow Mimram has ended in a little bit of an error, because I said that Pierce has, let me erase all this stuff. Pierce has gamma X returning the pair, but for this work, it has to return just the type. X colon gamma X should just return the type. Okay? Does that make sense? Yes, no, I don't know. Maybe it's hard to talk. You see, if I return a pair here, what I'm going to get is something that if instead I look up this, and then I'm going to get, what am I going to get there? I'm going to get, instead of B, I'm going to get X colon B if I put the pair in there, and that doesn't make sense. So this has to mean something different from what I said up here. It just is the type, not the pair. Okay. What if we do a couple more? Let's see. What if I have, we haven't really done any application yet. Let's do like, okay, start with the empty, show that lambda x dot X applied to, well, maybe let's start with, to simplify it, to start a little bit more simply, and to show you what happens if you start with a context. Maybe I say that Y is of type B. And here I'll say that this is of type B, and apply that to Y. So now I made it so that Y is the right kind of input to this. But what's the rule that applies? Well, the rule that applies is this one, because I've got something applied to something. So I've got Y colon B turnstile lambda B. Whoops. lambda tagged with a B. I'm sorry, lambda x, where the x is tagged with a B. I'm sorry, this is so annoying. I hate writing down these types, actually. That's got to have some kind of type. And according to the rule, it has to have a type. If I want this whole thing to have some type, this has to be a function type, right? And I know it's going to be a function from B to something, and then we can finish this off and could say, okay, y colon B turnstile. Oops. The rule says for the, so now I'm using this rule. I got to add x colon B to my context. And I got to show x has some type, but when I look x up in here, the rightmost x entry says it's a B. And then over on this side, so that means, oh, I'm sorry, it's not on that side. It's down below. So that means that this one is a B arrow B, but now I got to show that assuming that Y has type B, I got to show Y has some type, and it better be the input type here. So it has to be a B, but it is when I look it up in here. And so now I know that this term has type B. If I apply the identity function that's the identity on the type B to something of type B, I get back B. Okay, any questions? So I'm thinking that, like, I don't know, a fun thing to do would be, let's try and implement this. But, oh, I got to go back to mouse, right? So here we've got lambdas, except that now we need to modify this. So I'm going to say, write this out as simply typed. I can call it STL for simply typed ST lambda. STL is sometimes the name used for the lambda calculus. STL, simply typed lambda calculus. Okay, so here's lambda. And the only thing that changes is here is that I need a type. Can I have a type? And so it's either a tvar of a string. So I'm trying, what I'm doing is if we go back up here, what am I doing? I'm modifying, ooh, that looks funny. I'm modifying my definition of lambda terms to carry around the T as a type. And now I'm adding a type, and I need type vars. So I'll say tvar string, or it's an arrow of a type and a type. And then I've got, and then I've got like, okay. And I mean, it's often the case that you want show if you can get it. And you probably like EQ. And so now, you know, we can represent these as lists, but in the reverse order, right? Or we could do it as a map, right? Recommendations. I don't think I need the substitution, but I mean, it should work, except that I have to fix the type. Okay, so everything that I've already written that uses the old data type that didn't have the type in it will not work. Now, do I want to? Probably, I don't need, as far as I can tell at this point, I don't think I need any of this stuff. Okay, so now derivations. We'll just do these contexts as lists of strings, which is how I'm representing variables, together with a type. Yeah? So it's a list of pairs of string and type. And a sequence is a triple, which is a context, a lambda, and a type. Yeah. And so now what I want to do is I want to model these three derivation roles. And so there's one rule for axioms. So, I mean, is everyone with me? I mean, do you see what I'm doing? I'm modeling this mathematical description here in Haskell. Anybody have a question about what I've done? I'm just following the description here. Context. It's either empty, okay, and we'll get the empty list to be our empty context, or something of the type of context paired with a variable, a lambda variable, a computational variable, paired with a type. So we have a string is how we represent computational variables and type. Okay? And a sequence is just a triple. A sequence is a triple. Gamma T, which is a lambda, and A, which is a type expression. Okay. So, I don't know. Somebody say something. Kyle. I think of, you know, or Jessa or somebody. I mean, I know Finley. Finn is like a better Haskell programmer than I am. Keegan is a great and probably better than me Haskell programmer. So the rest of us are kind of like, okay, we got to struggle along. But so I need to hear from not Keegan or Finley, who are going like they're falling asleep, but from Simon. But see, Simon's not shy. I want to get Jessa. Are you really there, Jessa?
Yeah, I am.
Oh, good.
It's making sense to me so far
Okay, good.
on
Yeah,
the Haskell implementation.
I can follow along at the moment. There's a few things from last week I need to go over again, and I know we didn't have the video recording, but I think you had your notes.
Yes,
And
I will
would
put
be
that
useful
code
to
up.
see.
Yeah, I need to put that code up.
But at the moment, I'm tagging along reasonably nicely.
Okay. So to model derivations, there's going to be 3 kinds of rules that could be at the root of the derivation. And so the one is that we have an axiom and it just has a sequent. Right? The axiom rule simply has a sequent of a certain form. What about the arrow introduction rule? Okay, it has one sequent at the bottom and a sequent up and 2 other sequents above. So it has and then we have the arrow elimination, which has 1 sequent and 1 above. So this just models kind of like the raw structure, but now we kind of need a way to check whether we really have the right structure. Like you can't have something like the empty list paired with v of the string x paired with tvar a. That's a sequent, and it looks something like this. It's like the empty one and then turnstile x colon a is what this one would look like. But that's not actually an instance of the axiom rule because x and a aren't in here. So we would need to say, like, what does it mean to be well-formed? A well-formed derivation and if I have something like axiom and then I have a sequent, which is my gamma, comma, x, which is my variable name, and a, which is my type. And I want to say this is true if what? I want to say if like x comma a is an element of gamma. That's the only time this rule is true, is when this thing here as a pair is in there. So that one's pretty easy to write. What about, let's try the abs one.
For the x in the
Yeah.
axiom,
Yeah.
that's of type lambda. in the sequence.
Okay, so you're
So
right.
we
So
have
that
to-
needs to be a var. Thank you. Good eye. And so now here, the abstraction I've got now. I may need, but maybe not. Okay, so we've got gamma, and then I've got abs x type term or lambda, and this should be an arrow a, and now you can't reuse things in the on the left hand side there, so I got to say something like b, and so I don't want to cover the rule, but I want to have more room for my code. Whoops. Oh, come back. Okay, so what am I going to do here? So first, what I need to do is I need to make sure that, all right, do I have two sequence there? No. And so I have a sequent above. Gamma prime, comma, T1, comma, ty prime. I can't reuse B, right? So I think that that's, what did I do wrong? Okay, this is, okay, that's that. That's that. So that closes that. Now, see, this is where maybe, so I'm pattern matching in a pretty sophisticated way. I'm saying, look, the term, you've got a gamma, this sequence here is this. That's the first argument to the abs derivation. And that one is gamma. There's my gamma. There's my abs x a. Oh, maybe I should just call this a to match that rule better. And I could even call that m to match the rule better. And that'll maybe make it be easier to read. But see, now I can't use a and b there. I got to use like a prime. And maybe I should have a convention that for unknown ones, I just call them TY1 and TY2. But I do know it has to be an arrow. And I do know that TY1 has to be A, but that's part of the check. And so then up above, I have gamma. So now I'm looking at this sequence. I have gamma, but well, gamma prime, I can't say. I mean, maybe I could say it's a cons of something, but that maybe I don't need to do that. So I'm saying I got gamma prime, and that's going to be, I get a check that it really is this. And then I've got M, but, I can't use the same M 2 times in the pattern on the left-hand side of a definition. So I can't do that. And then so I got to give it a different name. And then I've got like a TY3. And so what are all the parts that I need? I need that gamma prime is equal to x comma a constant to gamma. And what? So this one up here has x comma a constant to it. So remember, we're working backwards from his notation now. And then I have that this m has to be the same as T1. And I have that Ty3 has to be B, which is Ty2. Is that right? Are you with me? So this one down here, okay, has to be, so what is Ty1 is equal to A. And what? Ty2 has to be equal to Ty2 is the second thing in the arrow. B has to be the same as Ty3. Are those all the constraints? Gamma's the right this. A is this. B has to match that, and that has to be the same as that. I think that's all of it. If those are all true, then I've got a good abs. What did I call the rules though? I said ax, and then this should be actually a intro. Or yeah, arrow elimination. Maybe that's why people are like confused, because I need to really do these rules. And so let's put the a intro rule in its right spot. Not that it matters, right? So a intros of the form S1, S2, S3. But I know that, for example, in S1, I start out, so S1 is really something that looks like a gamma. It's got this, and then it's got an app. Is it AP or APP in this code? It's AP. It's an application of what? Of, let's say, M and N. So this is what our S2 is oh, and I'm making a mistake here because these are uncurried, or I mean, they are curried. Right?
No, that's the sequent, which is a triple.
Okay. Thank you. Okay.
Also, in the previous rule, will we want to recursively call a well-formed derivation?
Absolutely right. We're missing two calls, or no, one call. Well-formed derivation on this one. Now, you know, I don't know if you know this trick, but I can say S at sign, and that means I could refer to this as S. So I'm working on S1, right? And so this is an application of what? Of, let's say, M and N. And the type is some kind of arrow. Oh, I'm sorry. I'm doing this rule. So it's just some B. And then this one above it to the left side is S2. And so that one's of the form gamma prime. So gamma prime, I'll call it, because I can't use the same thing. And it's M prime, but I can't use the same thing. And it's an arrow. And it's an A, B prime. I've changed my naming convention midstream here. And then what's S3 look like? S3 is a gamma double prime, because I can't use the same name, so I got to give it a new name, and then down in the code, I'll check that these three are all the same. And then N prime, and then A prime. Is that going to work? Yeah. And so now what do I have to do? I have to check that M is equals to M prime, and N is equal to N prime, and B is equal to B prime, and A equals to A prime, and that gamma equals to gamma prime, and gamma equals to gamma double prime. And well-formed derivation. And so now here I can write this as like S1 at S2 at S1 and well-formed derivation S2. All right, now what's the chance that this is going to load? So let me call this T1 M prime to now match my naming convention back up to be more consistent. And I'll call this like A and A prime. So instead of TY1 there, I'll call it A prime. And instead of TY2, I want that to be B and B prime. What do you think? You're going to load?
Did you meant to put B semicolon or B prime?
On which one?
So where you were doing the well-formed implementation, you've got B double equals B semicolon, but you're saying B prime. I don't know.
Instead of B prime, yeah.
For Haskell.
Do I have a B? Oh yeah, good. Thank you. That works. That's good. I don't think that's the problem there, but let's see. That's a fix. What is it complaining about?
It's also on the line down
Oh,
as well.
it's data.
Beneath that.
It's not type. No, this one has to be a data. Okay, let's go see what you're saying. It's also below. Yeah. So what's going on here? No comma. It's not into, it's intro, right? What did I do wrong here on line 7? I don't really need ORD, but why is it giving me trouble? Oh, because
it might be because type doesn't have ORD.
Do I need parentheses around this? Maybe. No.
I think the gamma got deleted from the parameters.
This should be a gamma, comma, right? Yeah. No. What is it doing? Do you see it?
The parameters are of type sequent, but then well-formed derivation takes type derivation.
Yeah, but isn't ax a derivation?
Yeah, but then the recursive calls aren't well typed because they're just called on sequence instead of
Ah, good.
derivations.
Okay, down here. Aha. Right. So this has to be, instead of a sequent, this has to be a derivation whose root. Okay. All right. So here's what we'll do. We'll say concal of all right, that's not going to work, is it? I'm going to have to actually do a match. Case, I'm sorry, I'm running over now, aren't I? All right, well, feel free to go if you need to go. This is not that pretty, but I don't know. Can you think of a better way to do it? Anyone? So here I've got all the variables matched up. Now I should be able to check these things. And then down here, I want to say case concal of D of what's going on? Did I call it D? The ALM rule has a sequent and another sequent. This is a sequent. And this is the other one. So what's the problem? Shouldn't be sequent, it should be derivation. Aha. All right, so now we have a way, and I'm sorry that took so long, but now we have a way to check whether a derivation is well formed, like that everything matches up as it's supposed to. Now, the next thing to do would be to build a derivation. And maybe that could be your homework. How's that sound? Impossible or doable or what? If I give you this, can you now figure out how to build one of the, given a context and a one of these church style terms, build a derivation.
I think we can do it.
Okay, so I will upload this right away. And your homework is to build a derivation. And I don't know, due next Friday. How's that sound? Okay, I'll stop the recording. If I can get out of here, stop share.